My source of inspiration is this spectacular city of Medellin Software Valley. Medellin Software Valley is nestled in a luscious avatar emerald green mountains of the South American Andes. These artificial intelligence ASIC semiconductors were developed at my design centers in Medellin Software District of Technology and also in Miami. The scope of this framework will present different design options for the development of ASIC system-on-chip design methodologies. In addition, I will delineate an open source ASIC design methodology using open source RF sources. These ASIC tools and resources include OpenLane, end-to-end ASIC flow, OpenRoad, Silicon Compiler, Coriolis 2, OSS CAD, Open Source FPGA, JOSIS, VTR, and VHDL support with GHDL. On the analog spectrum, I made use of tools like Magic, K-Layout, NetGen, NGSpice for simulation, GDS Factory, and OpenEMS. Physical tests were performed for LVS, DRC, CVC. At the LVS, each segment is built with OpenLane, which will check LVS for each segment of the project. Then I combine all the projects together to run a top-level LVS and DRC for routing, power supply, and macro placement. The extracted netlist from the GDS is what is used in the formal scan chain proof. DRC is checked by OpenLane for each small segment of the project, and then again at the top level when I combine all the projects. CVC checker is a device-level static verification system for quickly and easily detecting common circuit errors in CDL, circuit definition language, netlists. So I ran tests on the final design and found no errors at all. All of my ASIC projects go through a very rigorous verification methodology. However, in this specific example, I will split the verification effort into functional testing, simulation, static testing, formal verification, timing test STA, and physical tests LVS and DRC. First, set up the design. You'll need the GitHub tokens. For verification, I use iVerilog and CocoaDB. These tools are in the github.com Yosis HQ OSS CAD suite build. Go into simulations. simulation of at the RTL and GL level, simulation of the whole chip with scan controller, external controller, logic analyzer, check wait state settings, and check clock divider settings. With respect to scan controller, this test only instantiates user project wrapper, which contains all the small projects. It doesn't simulate the rest of the ASIC. So continuing with the scan controller, then cd verilog /dv/scan_controller. Next line would be make test_scan_controller. At the gate level, simulation requires scan_controller and user_project_wrapper to be rehardened to get the correct gate level netlists. Then you edit openLane_scan_controller over config.tcl and change num_designs to 498 to num_design 20. Make scan_controller and then make user_project_wrapper, then run the GL test, which will be under cd verilog /dv/scan_controller, then make test_scan_controller_GL. At this point, then run the GL test, that is cd verilog /dv/scan_controller and make test_scan_controller_GL. In single, just check one inverter module, mainly for easy understanding of the traces, that is make test_single. Then set up the custom wait state. Just check one inverter module, set a custom wait state value with make test_wait_state. Then set clock divider. Test one inverter module with an automatically generated clock on input 0. Set the clock rate to half of the scan refresh rate with make test_clock_div. Then top level test setup. For all the top level tests, you will also need a RISC-V compiler to build the firmware. You will also need to install the management core for the Caravelle ASIC submission wrapper. This is done automatically by following the PDK install instructions. I also need to install the management core for the Caravelle ASIC submission wrapper. This is done automatically by following the PDK installation instructions. Top level tests. Internal control uses the scan controller instantiated inside the whole chip with cd verilog /dv/scan/controller.int. Make coco_tests. The top level tests. External control uses external signals to control the scan chain, simulates the whole chip. Then the top level tests. To use logic analyzer control uses the RISC-V coprocessor to drive the scan chain with firmware and simulates the entire chip. Then formal verification would be formal verification that each small project scan chain is correct, and the formal verification that the correct signals are passed through the 3 different scan chain control nodes. The RTL was successfully developed for this ASIC/FPGA system. After functional verification, we also synthesize the unit into a gate-level netlist. Then timing verification was performed to verify that the system on chip multi-core system meets timing requirements. Once the design meets timing goals, the netlist is given to the physical design, which places and routes the design, and then finally the chip is built and tested. The high-level system design process applied in this design was as follows. First, I identified the system requirements, followed by writing the preliminary specifications and parameters, thus developing a high level of algorithmic models in both C and C++ and also in VHDL. After that, I refined and tested the algorithms and determined the hardware and software partitioning at a system high level. Then I defined the interfaces and the software specifications were written and to develop the prototype of the software. The hardware-software co-simulation was also performed, and the hardware specification was developed with behavioral models for the system. The partition was developed with reference to macros. Several macros were developed, and the preliminary specification was written for those specific macros. At the top level HDL, I successfully determined the configuration and generated the top level HDL design. In parallel, I completed and generated synthesis scripts, synthesized with reference to the library, provided scan insertion, ATPG fault simulation, and also perform the final timing and power analysis. Also in parallel, provided functional verification with a reference simulator, developed and ran multiple test configurations, and measure test coverage. For those sections of the design that are full custom, we have the choice between manual porting and automated porting. Under certain circumstances, automatic porting tools such as Gigantic Dream can be effective. These tools operate at the polygon level, automatically mapping transistors and interconnect from one set of design rules to another, and shrinking the design as much as possible. For large macros such as multi-core embedded systems, where simulation speed in the system environment may be an issue, it can be useful to include cycle-based simulation and/or emulation models. In general, RTL that complies with the coding guidelines will work with cycle-based simulation and emulation. However, test benches and bus functional models, unless coded to the same RTL guidelines, are important and effective for large macros. The product files, in addition to the RTL in Verilog and VHDL, we must include the synthesis and installation scripts. We include the reference library so that we can synthesize the design and verify that the installation was completed successfully. In addition, providing the reference library, scripts, and verification environment allows us to create this true environment. Porting the hard macros. For hard IP that was completely synthesized, the porting strategy is quite straightforward. We just resynthesize, targeting the new technology library, and repeat the physical design and timing model generation. Verification files. The entire verification environment, including any bus functional models, bus monitors, or other models, and some set of verification test cases are included with this design. The integrator then develops a test suite to verify the functionality of the macros. So the bus functional models used to develop and verify the macro can be used by the integrator to create a test bench environment for the system on chip unit. The arithmetic logic unit is capable of calculating the results of a wide variety of basic arithmetic and logical computations. The arithmetic logic unit takes as input the data to be operated on call operands and a code from the control unit indicating which operation to perform. The output is the result of the computation. So the ALU, the arithmetic logic unit, will perform the following operations. The arithmetic operations, that is addition, subtraction, increment, decrement, transfer, logic operations such as AND, NOT, OR, NAND, NOR, exclusive OR, and also exclusive NOR. The objective is to show the implementation of a 32-bit arithmetic logic unit using the behavioral model style to describe how the operation of the arithmetic logic unit is being processed. It is accomplished by using the hardware description language, the VHDL. The behavioral style makes use of the process statement. The process statement, which is the main construct in behavioral model, allows using sequential statements to describe the behavior of the system over time. So a process is declared within an architecture as it is illustrated in this video and is a concurrent statement. The statement inside a process are executed sequentially. So the process reads and writes signals and values of the interface, which is input and output ports, to communicate with the rest of the architecture, like other concurrent statements. As I have illustrated and shown in this video of the arithmetic logic unit, I have used several constructs to model the VHDL process statement. Also, I have used the when statement. In the case statement, it executes many sequences of statements based on the value of a single expression. Also, the case statement evaluates the expression and comparison of the value of each of the choices, while the when clause statement corresponds to the matching choice, which will make the statement to be executed. Part of the ASIC System on Chip (SoC) design methodology is the functional verification and the manufacturing test verification. Therefore, my objective is to illustrate the SoC verification paradigm from a conventional verification process and Universal Verification Methodology (UVM). Split transactors. So the objective is to move as much of the UVM test bench code onto the accelerator or the emulator box in order to speed up simulation. This means splitting each transactor, that is the UVM driver or monitor, into two parts: a lightweight proxy or a wrapper that continues to run on the host, and a synthesizable part, which is the BFM or bus functional model, that runs on the box and wiggles the pins of the device under test, the DUT. So in order to accomplish this task, the code has to be structured into two separate domains: an untimed HVL domain that contains the UVM environment or verification environment, and which must not contain any delays or clocks; an HDL domain that instantiates the DUT, the device on the test, and the synthesizable parts of the transactors can be run entirely within the box. The synthesizable test harness contains code to generate the clock and the reset, and the code to instantiate the bus functional models, the BFM. So the pin level interface and the DUT. The untimed test bench instantiates the UVM environment. So it is important to note the untimed test bench is that the virtual interface within the top level configuration object is set to point to the BFM interface within the test harness, that is top underscore HDL underscore th.bus underscore BFM underscore 0. This is a full hierarchical reference to the interface instance of the bus underscore BFM underscore 0 within the top level module. So when the UVM driver and monitor proxies communicate with the code outside the class-based verification environment using local virtual interface variables, they will actually be communicating with the BFM in the synthesizable test harness. The UVM code generator interface template file contains settings to include various user-defined code fragments required to define the UVM driver, such as the proxer or wrapper for the full driver transactor, much of which is implemented on the HDL side in the synthesizable bus functional model, BFM. Now I will talk about the test plan creation in the universal verification model. The tests are applied to the DUT and fed to the signal generator to generate the input to the bus functional model, that is the BFM, in order to drive it to the DUT device under test. The input monitor collects the status from the BFM, the bus functional model, to the DUT, and the output monitor collects the response out of the DUT, as it is illustrated in the system block diagrams of this presentation. The input packet and the output packet response is fed to the scoreboard and checker and compares the response from the DUT device under test and the reference model output. The build phase and physical connection of all components are done through the test generator, or the test generator, and of the packets to the BFM is the most time-consuming of the verification process. And the run phase collects the process from the device under test into the output protocol monitor and calls it in the scoreboard, as you can see from the block diagram, to run the test cases on the device under test. If the test case or the test cases are clean, then you can report the results and get an actual report.